I'm going to explain the difference between strong and weak acids and bases. And I'm first going to give you a list of the common strong acids and strong bases. Um, Strong acid, hydrochloric acid, sulfuric acid, so four right there, nitric acid, um, hydroiodic acid, hydrobromic acid, and HClO4, which is perchloric acid. So these are the common strong acids. Common strong bases are going to be lithium hydroxide, sodium hydroxide, potassium hydroxide, so basically all the alkali metals. Then in the alkaline earths, calcium hydroxide, strontium hydroxide, and then barium hydroxide. So these are the common strong acids and bases. So looking at them, you can tell that, you know, yeah, that's an acid, bunk, chunk, all the way down, and oh yeah, that's a base. So these are all best defined in terms of Arrhenius acid-base theory, because these acids are going to give up hydrogen ions. These bases are going to give up hydroxide ions. So now, what are weak? Well, weak is everything else. So weak is a lot. A lot of stuff. And so I'm going to show you how you can tell the difference between a weak and a strong acid. And basically what it is, and I'll just do it right here, weak are in equilibrium because they do not ionize 100%. So they ionize, and ionize is when the hydrogen or the hydroxide comes apart, ionize less than 100%, whereas with the strong, these guys all right here ionize 100%. So let me show you how that would look in an equation. For example, hydrochloric acid is a strong acid, okay? It ionizes 100%, so I get hydrogen ions and chlorine ions coming out of that. Now I could have incorporated water into that same equation and it would have been exactly the same thing. I could have written it this way: HCl plus H2O going to H3O plus Cl minus. These are synonymous. These are the same thing. They're the same because this critter in acid-base chemistry is the same thing as that critter. All right? But the point is, these are strong, and they are strong because they ionize 100%. Meaning, okay, if I have one, for some reason it's not drawn up there, so let me get rid of this guy so I can draw on top of it. Okay? Get rid of this thing, come around here too. Sort of. Alright. Because it ionizes 100%, if I have a 1 molar solution of hydrochloric acid to begin with, I'm going to end up with an acid. Make that arrow better. I'm going to end up an acid that has a 1 molar concentration. And I'm also going to get a 1 molar concentration of chloride ions, but they're spectator ions and nobody cares about that. So if I were to say, in a question, what is the H plus concentration of a 1 molar solution of hydrochloric acid? Okay, the first thing that I would do is, it's hydrochloric acid, so my decision is, since it's hydrochloric acid, It's a strong acid, so therefore I know that it's going to ionize 100%. So if I have a 1 molar solution of it, that is going to produce a 1 molar solution of hydrogen ions. All right? Now let me show you what you do with it when it's a weak acid. The weak acid I'll pick acetic acid, HC2H3O2. Now when it ionizes less than 100% because it is in equilibrium. So I give the two equilibrium arrows. I'm still going to get the same thing coming out of it that makes it an acid, the hydrogen ion, C2H3O2. Let me get rid of this thing. Not sure where that came from. There's a negative charge on that. All right? But in this case, if I start off, okay, number one, it's in equilibrium, so it ionizes less than 100%. If I start off with 1 molar of that, I don't know exactly how much of this or of that I get because it's in equilibrium. I do know, though, that the concentration of the hydrogen ions will be the same as the anion that came off of it. Those will be the same because for every one of these that came out of it, I get one of those. But I'm just going to call that X for right now. And since it's in equilibrium, I can write a mass action expression. The mass action expression is going to say that the hydrogen ion concentration times the anion concentration or the acetate concentration over HC2H3O2, my original concentration, is all going to equal Ka. Well, Ka is a published amount, so I would go look that up in a book. Ka would be 1.8 times 10 to the negative fifth. That happens to be the equilibrium expression constant for acetic acid. Ka, that little a right there, that's supposed to be an A, designates the fact that it's an equilibrium constant for an acid. A base would have a Kb. Same thing though. So now if I go through and solve this, it will be X times X over 1 molar. Okay, I just plugged that X for right there, that X for right there, this 0.1 molar for right there, substitute it all in, and now if I go through and solve it, to solve this, it's going to be X squared will equal 1.8 times 10 to the negative fifth. So then X is going to be equal to the square root of 1.8 times 10 to the negative fifth. And if I do that, I get the hydrogen ion concentration, H plus, not really writing so great down there, equal to 0.004 molar. And it is weaker, okay? I mean, there is less. For an equal concentration of 1 molar, 1 molar concentration of a strong acid gave me 1 molar concentration of hydrogen ions. So I had sort of a glitch there, so I'm not sure exactly where I stopped talking, but what I wanted to talk about was that when I had a 1 molar concentration of the strong acid right here, that gave me the hydrogen ion concentration of 1 molar. Now here, where I had a weak acid, 1 molar concentration of a weak acid ended up giving me 0.004 molar of the hydrogen ion in solution. So that was consistent. Weak ones don't produce as much hydrogen ions in solution. Now, had I used this equation right here that incorporated water into the mass action expression, same thing would happen. Remember that in mass action expressions you don't include liquids, so that wouldn't be in the mass action expression and everything else would work out just fine. Try this in class.